Just to update that what today I wanted to share with you in about 90 minutes from now on is talking about what is this about, like what is molecular modeling, why you need to do this, or anybody want to do this, and the solution portfolio what we have. And we'll give some of the examples in chemicals and composite, because materials are many. And we do cover by molecular modeling the whole range of materials. So this is not just limited to chemicals and composite, but I'm kind of highlighting this. I'm sorry, is that a question? Or you can mute yourself. Can you mute yourself? Okay. And then the conclusion and to give a key takeaways. Okay. So I think we all know why materials are important, right? So if you see in the screen what you are showing here is, you know, the material started at the age of at the Stone Age, and these ages are called Stone Age, Bronze Age, Iron Age, and as the name it says, it is the materials are only available, and those materials to be used to make something, right? So in the Stone Age, the only material available was stone. In Bronze Age, it was bronze, or in Iron Age, it is iron. And so there is no material choices. So even if you have to make a car at that time, then you have to use stone, or if you have to use bronze for making a paper, for example, if you wish to make. But things has changed now, right? So from 500 AC to now, every day I think is coming up new material for a new specific usage. Think about it, how materials, even if you 10, 15 years, you might not have thought of. Certainly from iron to steel, there are plastic, which is polymers, there are glasses, which are mixed materials, there are concrete, which uses lots of organic organic compound to give them binding, make them less water taking. There are composites, and there are many materials coming up every day. So there is a change in the concept. So earlier it has to be the material, so you have to design things based on that material only. That means if you have wood, you have to design this kind of like a windmill. If you think of this is used for pulling water, and this could be only made by wood, because wood is the only material. But on the right hand side, which is now, you think of that you need to make something over sea. It should have sea water, because you need the wind. You want to generate a windmill with that wind, and it should be not corroded. It should last in the water. It should be lighter. And then you decide what material you choose. So the concept has been changed, right? And that we all know. And why this has been a change, and these changes are very dependent on the things what we are having, right? That means, and I give you 4 bullets, and I do not want to make it red, because it's not just like not something an obstacle, but just to tell you that how things are changing now in the material world. The basic change which happened was regulations, right? You cannot export or import any material you want to use, right? For if you are using refrigerator, and if you are using fluorine, then it is restricted. It could be restricted that you cannot use those refrigerators which are 30 years old. There are regulations that you cannot transport one from Thailand or from Asia to Europe, anything with fluorocompound. That's a regulation. You have to change something to a new material which to be used. There is a growing competition. The competition was there before, but as we all know that now no single company make a single material, right? And certainly there is a tough competition to everybody wants to make the same different materials, and also the material where the business is. So how one company wins from another? They have to win the customer, right? And to win the customer, there is a change in the demand, because the customers are becoming very smart. In earlier days, as there was no plastic, any plastic bag was good. As there was no plastic, any plastic shape, any plastic cup, bottle, whatever you want, you can use it. But now, people do not buy anything plastic for your drinking water. They will say if it is BPA free. They will not use any bottle which is not biodegradable, which is hard, which cannot be melted, which cannot be waste properly. So, and the customer is looking into, if you see your kids, I think they're smarter. They probably will first of all have a look into the bottle to see, what are the ingredients, where from they're coming. And this is impacting the business because you cannot use any material now. And certainly resource instability. We have seen this in the last 2.5 years, what COVID can bring us to us, right? And it's just not COVID, but it's also some other instability in which comes from geopolitical situations. And based on that, what people are wanted to do is to go sustainable. This is a key word in the sense of that we should be doing things greener, right? We should save our planet. And then we have to implement total quality. We have to cut down the innovation cycle so that I can make the product faster. I can beat the competition, but I should be green and I should be saving money because, we have to be profitable. And finally, to do that, I think the most important thing is that people are now looking into the data, the knowledge. As we all know, that experience gives us a knowledge. And the experienced man, if he is not there, then where goes his knowledge? The knowledge goes off when the experienced man retires. How can we capture that? That knowledge capture means it's a data capture, right? And so that's very important and what the people are trying to do. So the whole idea is to do a research, development something, then you scale up, you manufacture, and then you do a quality compliance. So if you think about research, and that's what the focus of this talk today, it's not about manufacturing. It's about how do you find a new material? How do you change a material based on the property you want? You want a plastic to be having more thermal conductivity than the one which you're using. So you need to know what ingredients you will change or what process parameters you will change to get that property. So it's a finding candidates, right? And the finding candidates are so overwhelming that you might are not able to do that experimentally. The second thing is once you find a candidate, you want to evaluate the candidate. Evaluate means what is the properties it can do, right? Is it complicated? Is it difficult to synthesize? And they're also not matched to sustainable requirements. And finally, your material structure to performance should be linked. And R&D output does not meet the needs of manufacturing. So the manufacturing says that, it should be, you cannot make something very fancy to do a manufacturing, right? That, by fancy, you mean that you have to have a very sophisticated instrument to make a material, then you're out because it's not cost effective. You probably will have to do some specific treatment where you need skilled laborers, you're out from the manufacturing. So these constraints are there, and so it is the bottom line is it's expensive. Its lab capacity is not optimized, marketing requirements are not met, and products fall in manufacturing. And this story is not just for material manufacturer; it's also for academic, because in academic you're trying to find out new material for specific application. So how do you solve the material challenge, right? So it could be a new resin. It could be optimizing a catalyst. It could be finding out a better solvent. Whatever you do, these are expensive. They're time consuming. They are small sets. And I'm just giving some examples. And I think you know more than me about what is the cost of doing experiment. So this is what we are getting from our users. That to do a tensile testing, it costs you per sample $50 to $125. That means it's involving the machine, involving the sample you have to make, and the process, and the person's labor, and all these into consideration. It could be $300 to $420. It's not, don't take me that 420 as 20, but something like $300 to $400 for doing a TG calculation, glass transition temperature calculation. You're a polymer guy, You probably know that's the temperature of the plasticity, right? So, and this is the cost of one data point, and it does not include the synthesis cost. So it's costly, right? So what we provide is, it should be best that either you do some machine learning somewhere, your existing knowledge, you find out the white space, you do some simulation to design experiments, and you conform in the lab, and that's the loop. You do not first do any experiment. You first test it in the simulation, you generate the number, you find out the best candidate, maybe 2, maybe 4, maybe 5, and then only synthesize those 5, apart from synthesizing the hundreds of them. And then suddenly you then go to aggregation, project, cost, and all these things. And this is done by computational material science. That is what computational material design or computational molecular modeling does to make molecular faster. And I'm just giving you the revolution it happens in the materials world, right? You know about these bottles, and I think I'm not exactly remember that if you have it in Thailand, where I was very frequently traveling because of our users there a couple of years back, that you can serve alcohol in plastic bottles now. You can serve different color bottles, which is where you want to reduce the sunlight, and this could be made by the plastic now we generate. You can see artificial bone. You have seen vehicles, EVs, fuel cells. You've seen the cover of iPhones, Androids, and the designs, the cameras, and it's all new material. So what is computational material science? It uses modeling, simulation theory and informatics to understand the materials, right? So that's the point, and we use some theories, physics theories, and apply chemistry there. So the idea is, select a candidate, screen in silico, select a candidate, pass it to synthesize, analyze, test, does not work, come back and figure out what's the reason. And that's the cycle which we normally do with molecular simulation. So okay, what's our portfolio? What we talk about here? So basically, molecular modeling, where we are using, it's called the software platform. What we provide is called Material Studio. It's a comprehensive solution for material designing. And as I said, the only requirement to do molecular modeling is the material structure. You cannot tell me that I have a piece of plastic, but I don't know anything about that, how this plastic made. But plastics, we know that there are some materials, how it mixed. But we need to know what is the material. It cannot be just, even if it's wood, it's cellulose. If it is coated with something on the cellulose, then we need to know what chemical, what solvent, and all of these structures, we have to create a molecular model of these structures to run these calculations, okay? And I will explain the calculations. The calculations means estimating the property values from there, right? And I know this is after lunch, but it's like, I just wanted to show you that this is the whole scale is about. And the scale means we are talking about different properties, and we are talking about what sort of sizes we are looking into, right? So, and as we know that this is your device, this is your finished product. It could be car, it could be a cosmetic, it could be a polymer packet. And so if you think about it, going into that, then the step before will be a process modeling or a continuum scale. This is where the macro scale exists at the device scale. And the device scale uses lots of different physics-based equations like Navier-Stokes, or Fick, or Newtonian law. And we use also some physics-based equation like Schrodinger equation, Hartree-Fock equation, to calculate different properties, right? And these are methods. Quantum mechanics, where we wanted to see the electronic structure calculation. The molecular mechanics, which is looking at the molecular force-based interactions, van der Waal, electrostatic, and then the mesoscale. And suddenly anywhere there should be a machine learning. This machine learning, where we can put, depending on where do we have the data. If I am starting from a white space, then I have lots of data. I start machine learning in the beginning. If we have more data after calculation, then I put the machine learning somewhere in between. But machine learning should be a part of it, because you are screening You are generating data, and you should be able to use some artificial intelligence so that you can properly use the data, properly use your knowledge, right? That something is very important. Now, a little clearer picture, okay? We are talking about scale, so how it looks like. What is the difference Material Studio is bringing into the table? So all modeling tool requires a modeler. It's called visualizer. It's a modeling tool. What does it do? Like, what is it for? Here you can draw molecules, right? You draw three-dimensional structure of a molecule, a polymer, a crystal structure. You can make a surface, you can make an interface, you can, and also then you choose what properties you want to calculate. You thought, okay, I want to see the NMR chemical shift for a zeolite, or an NMR chemical shift for a polymer to understand the structure, and I run some calculations with say quantum mechanics, and after that the results come back inside the visualizer. So you can pre and post processing are done by visualizer. So you need to have a visualizer as a modeler, and then you choose. You can choose if you are an expert user, you know what you want to do, what kind of theory you want to apply. Then you can tell us that, oh, I want to use quantum mechanics, and I want to use, like properties like, as I said, NMR, IR, Raman. And these, whenever I talk about these spectroscopy needs electrons. So there are electronic movements. This cannot be done by anything else except quantum mechanics. So I will recommend you. Now, why so many quantum mechanics tools? Because it depends on different applications. We make different algorithms to calculate some properties. It's a special algorithm to using some sort of a specific functional form, or I should say a specific expression, and we call it basis function. It could be, depending on that, we could choose. If you are doing reactions, we'll propose a module name and ask you to use it. And similarly, if it is molecular mechanics and you are not interested in electron, you are interested in forces. Where actually, like polymers, I want to see how the polymer adsorbed over a surface, and then I pull the polymer from the surface, and I want to see how the breakages happens. What is the stress strain behavior? I want to see thermal conductivity. I want to see the mechanical properties, and these systems are pretty large because polymers can be with a molecular weight of 20,000, so it has many number of atoms. And quantum mechanics has a constraint that it will take a computational time in terms of solving these Schrodinger equations. Whereas molecular mechanics is simple, it does not contain electron, it is considering only the forces, so it can be used for a larger system. And then you can go a little bigger, as you remember. So this is something about 10 nanometer, this is 100 nanometer, this is micrometer, right? So that's the scale we are talking about. And then it goes to millimeter, meter, right? So this is mesoscale. This is from 10, 100 micrometer, and we also have some statistics based method for calculating structure property. Okay. So what you can see by molecular simulation. So the input requires is the structure, any structure, and I will show you in demo what do I mean by these molecules. I make these molecules and I ask Material Studio. I use this from the software. I pick up a desired software and calculate this, run this calculation in the client or a server, and get the results so that I get the properties understandable. Okay. And so if you see, this will be the molecular Material Studio, how it looks like inside. It looks a little better than this of this slide. And your idea is that you're looking at new material, or you're looking at new functions, and so you're validating your ideas, or you are trying to understand and confirm some behavior. That, oh, this polymer should have been interacting with the iron, and it is to be broken. Wow, yes, I can see it. Or I thought it should be happen like that, but actually I did not expect that there should be also some porosity in iron oxide surfaces. That kind of, so there is a question and you try to find out an answer for it, right? That's the whole point of it. So why people are using it? I think as I was talking so far, you can understand that this has been used for new material development. To ask yourself, do I do new material? You may say, oh no, I mean, yeah, but I just buy some materials from different vendors and mix it up and try to see. But you don't know what you are mixing, how you are mixing, what is the dependency. So you can do those tests by themselves and tell your vendor or somebody from your buying that, you know, this works, but I think if you put a little bit of fluorine there, or if you have a functional group with carboxylic acid, it may help because it gives some acidity. But that's what the simulation is telling me. So you can guide it, right? So first of all is screening, new material development. The second one is where I do not know what's happening. I want to find an answer. And the third one is to combine these properties to a larger scale. So I calculate a property from a nanometer, micrometer scale. I want to use this property into a macro scale so that the macro scale will contain the material property, the new material property. So that sort of connection will give me a more reasonable value for a larger system. Okay. So the basic idea is that it's lower product and lead times, it reduces cost, it improves the process quality, it solves critical research problems. And it has to be and I think this study, it's an IDC study, chemical industry market study. So and this is for industrial customers or industrial users who has to defend that, you know, why you are buying a technology, why you are buying something, what's the value, what is the KPI. So the value of this is you're not doing any real testing. You're doing a completely virtual testing, and you are trying to understand the properties with some accuracy. And when I say some accuracy, in some calculations, the results will be very accurate. Some calculations, it will be little less accurate because not every properties can be calculated accurately with the limitation of the theory. With the model, but those we can calculate or we produce, we know what sort of error we are having in these results, so that you can quantitatively define that and use it for a reference. And there are multiple properties can be calculated: adhesion, morphology, adsorption, diffusion, spectra. You talk about adsorption energies and a lot many more. Now, this is the slide where we talk about not just to show that who are using it. You know, maybe they are, these are few we put in this slide to show that, yes, this has been tested and validated by many users in the industry, and also very large we are in the academic. I'm not sure if there are a couple of you have met me or met somebody who with Material Studio before. But and you could see that these, what I wanted to emphasize is that this is, if you wanted to use Material Studio to generate value for your usage, either in an academic institution or you are a commercial entity, the KPI, this is to show that this software is stable and so many companies are using it. So if you wanted to use this for your research for R&D, or an academic, you want to explain the behaviors from the for using simulation, then this could be it, because that's a validated, tested environment. And you will see here that we do publish a lot. And I think this name of Material Studio is now 21 years. This is our 21st anniversary, I should say. We used to be, our name was BioSim, then MSI, we were called Acceleris. Because earlier we used to acquire company, and now we have been acquired by Dassault Systems in 2014, and so we have changed our name to BIOVIA. But the product name does not change at all. And you could see also that we have so many publications you can search for, and I'm just putting a website. You can use that website to find out references you're looking into, because you may be doing something else. You may be looking at oil recovery, for example, or you may be doing catalysis, and these examples I have not covered. So you can go there, search catalysis, and it will show the references which have used Material Studio. Okay. Then I think it's a series, right? I mean, I don't want you to look into it, but we provide a comprehensive molecular modeling tool in one platform. So you do not need to have change in any format for any of these modules to calculate. So that means today you are doing some density functional or DFT calculation, and tomorrow you want to use something on molecular mechanics. You can use this structure and run it in molecular dynamics. You do not need to convert. You do not need to do anything with it. It is over the Material Studio platform, so it does not require any sort of format change or do something. It is non-readable. Neither these programs are you will be compiling on the computer. These are all compiled. You will see that when I show a demo. Okay. And there's another tool what we have. I will probably not showing examples or going details on it. This is mostly on liquid properties. If you're using many different solvents, and solvents can be used in polymers, in petrochemicals, in coatings, in fertilizers, in fragrances, in food and beverages, in pharmaceuticals. The solubility is a very, very key phenomena which is happening. And this solubility can be dictated or can be calculated. The thermodynamics of the solvation can be calculated through these tools called Cosmo. Term it used to be, it's called now solvation chemistry. And so that could be a very useful tool if you are working for any of these industries, or maybe you can tell me some other industry also where there is very important of the solvent to mix to do something on it with the solvent. So with that, I will just go to the examples. But before I go to the examples, I think I just wanted to show you Material Studio, how it looks like. So I will open up Material Studio. And just to tell you that you see here Material Studio 2022. So the Material Studio is something what we have update every year. And Material Studio needs to have a Windows environment. It should be Windows 10 or 9 or 8, because we support 3 versions of Windows, because Microsoft changes and then we have to accommodate, we have to test our software. And so then you will start, and once you have the Material Studio in Windows, and then you can run the calculations in the server. Either that could be Windows or it could be also Linux. Okay. So you get into this sort of interface, and you want to create a project. That project means what you want to do today. You can put a name. You can also put what do you call it? A structure, whatever you want, right? It does not really matter that whatever name you put, but you cannot use anything except English. Okay. And you find out this sort of an a kind of interface, right? So that I will make it bigger so that you can have a little bit of better view. And what you see here is that it has a upper part where you draw your molecules. You have a part where you understand the properties. This is where you submit the job, and you will see what job, where you are running, how you are running, and all other details, right? Okay. So so as I said, and so we provide you a tool where you can draw stuff, right? So whenever you want to draw, you have to decide that how you want to draw, because these are atoms and molecules. So you may want to draw them like ball and stick, or you want to draw them with a ball, whatever you want to do. So you decide that, okay, I want to use the default atom style. I want to draw them with ball and stick. So my atoms will be ball and the bonds will be stick. I can change the size and whatever I want. And then I go and say, okay, let us make it. So we provide these many different things to use in Material Studio. So you can draw a 3D atomistic document. This is a 3-dimensional structure you're drawing. You can also draw a mesoscale structure. You certainly can write a memo, an HTML. We also provide tools to draw something by a graph. So you don't need Excel. If you have it in the computer is okay, but you can just draw small graphs. You can see the structures with the data. You can also write a script. This is a Perl, it's a language. You can write Perl script. So maybe some of you are interested in doing programming, both in academic and in commercial institutions. Then you want to use Perl as a scripting tool. And there are also something of a force field manager. But let us focus on the 3D isometric document. So we are drawing something here, right? So and the most interesting thing is when you draw something, there is an axis. So you know from which axis you are seeing, and you can rotate the molecule to see how this molecule is rotating or changing structure, changing the conformation. So while to draw a structure, you need a pencil, right? So it's a pencil, and I have atoms. So I can choose. These are regularly used atoms. So if you say hydrogen, carbon, nitrogen, oxygen, chlorine, if you think, no, I actually want something on a periodic structure or some other elements, then I can choose it from there. I will stick with carbon, right? So I will put a carbon, 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 carbon. I thought, no, actually, you know what? I have a benzene ring there, so I can want to add a benzene ring here. I want to add, okay, I added benzene ring, but it should be all hydrogenated. I click on hydrogen. No, but I want to have a functional group. So I can go here and say what functional group I want to draw. So I go here, I choose the functional group. I will say functional group. I can choose, I say, okay, let us have a carboxylic acid, right? So this is carboxylic acid. I click it in the ortho position. I stop it up, and this is my molecule. But this molecule does not look, there is some constraint here. The angle, the bonds are not looking like a normal bond. So I have a tool called Clean. And what it does is it will look into a database and confirm the carbon-carbon bond lengths, carbon-carbon angle. Most of the data are there of a regular molecule, so we can just clean it, so it will make it look better. I want to make it at the center. I want to see by rotating it. I can rotate it to see how it looks like. I can see the screen so that I know which axis I'm looking into. I can zoom it so that I can make it smaller, bigger, whatever I want. I can also do a moving of these in a vertical direction, and I can come back to that. And certainly these are very unique, very easy to use in that sense that I want to change a bond. I go and click the bond and I say I want to make it a double bond. I click somewhere. I change it to hydrogen so that it automatically changes the hydrogen. You don't need to do anything there. You want to say, no, it's okay, but I wanted to have an oxygen here, so I can have a change in atom. I change oxygen, it changes color. Then I say, okay, I wanted to see the bond, so I clean it up. Then the oxygen bond little increases. I can put an hydrogen, so it will put an hydrogen. Then I clean it so that may be a little different from the other side. So this is like a molecule, drawing a molecule, right? And certainly once you have this molecule, you have not done anything with it. But I think then you need to see what actually is this conformation. It looks like it is pretty strained, right? There is a big torsion here. And let me better see what is the conformational conformation there. So I then, from the Material Studio provide these 25 different softwares. And you have to tell me what you wanted to do. I mean, tell me in a sense that, tell us, and so that I can recommend you which software you are going to use. So I will just choose that a conformation, right? I will go and choose conformer. I will say calculation. And I say, but what I wanted to calculate was, I want to see the torsions. How many of them are there, right? And I wanted to see, including the terminal bonds, terminal hydrogens, and say, okay, fine. So if you see it, it is finding all the torsions except the ring because it's constrained. It does not change. And you see there are torsions here, and these torsions are important because that's something detrimental. So I say, okay, I wanted to look into this torsion because to me this is important because this hydrogen and this hydrogen is very, very close. And certainly I want to see therefore the adjacent torsion. So I can see all of them, right? I can do this and this. So I can just shift this and this, and the rest I can delete, right? So I can say, the rest of them I probably not do it now today, but I will do it later. But now I think I wanted to do this one, sorry, I want to do this one and this one, right? So I choose these two and I say, okay, so this gives me 36 configurations. What I'm changing is I'm moving these torsions slowly. So I can do it now at a 60-degree angle, and I'm doing it from minus 180 degree to plus 180 degree. So I'm covering a 360-degree range, and I want to say, oh, you know, make it 10, right? Make it 10. Make this, so I'm reducing the angle. So I can certainly use it for very, very large or very, very small angles to look into it. So what I'm getting out of it is it will be running this calculation and will tell me what is the energy of it. And I have to use some sort of parameter, and I will go there with the force field. The force fields are experimental parameters mostly. So what is the parameter means is these are the carbon hydrogen bonds. So you have to have some interaction parameter between carbon and hydrogen. You also have to have hydrogen and oxygen, which is not bonded, or oxygen and carbon, which is bonded. So each an individual geometry parameter to be defined. And these are called force fields. We provide you many, many force fields, about 10. But we say compass is a very accurate force field because we do not use experimental data for making those parameters. We use quantum calculations to calculate the charges and the bond distances and the angles and make those. So I will use compass, and I will say force field assign. So I use the default values. I will say energies, and I will say please run these calculations. So it will be running 100 conformation based on these two angles. I can run everything. For sake of time, I'm not doing it. And it will give me the lowest possible structures when we have varied two of these angles and each of them at 36 degrees each. Okay. So if the calculation is now submitted, you know what calculation you have submitted. It's a conformation calculation. It is running in a local host, that means this machine, and it is running now. And you can also see when this has been submitted, like, you know, it has been submitted here, and the calculation finishes in a few seconds, right? And this is very, very important if you're a polymer scientist and you wanted to see the monomer. You are building a monomer, but you have to know the structure of the monomer. And so I have seen these numbers, 100. How do I know which one is the energy lowest? So I select a line, which is the energy, and then I say, please sort descending. So that means the upper one will have the highest energy, and the lower one will have the lowest, right? So I go there down and then see the lowest energy. So this one is having the lowest energy in terms of this configuration. Okay, wow. Okay, so you see now that the molecule which we have drawn, and I will just bring this as a reference. And sorry, there are a lot of things, so I will just stop this up. Just as a reference so that you can have a comparison. And this is something what we had. And so this is your initial configuration, right? Sorry, this one is your initial configuration. You see these two hydrogens are pretty close, right? And if you want to see them, and that's the value of some simulation between this and this. So you see, this is 0. If I can see you, if I can make it bigger, it is between 2.040 is the distance between these two. Okay. And if I run this now between this and this for this system, right? In this case, so I will see that there is a change in the distance, right? So you're looking into OH, right? This H, and you are looking into the carbon hydrogen, right? Right, and you see this distance has been changed to 4.2628. So there is a drastic distance change because this molecule has rotated completely to a different, and you do not know this by just drawing the molecule. Okay? So okay, I have now a monomer. So what should I do with it, right? So I want to make a polymer. Okay, yes, that's the interest, right? So I remove this. I remove all these levels because I don't need them. And then I say, okay, this is my monomer, but okay, so let us now build a polymer with it, right? How do I build a polymer? So build a polymer, it requires a repeat unit to define. So if I choose a head atom, this will be my head. I can go to the end and say this is my tail. I can also say this is my tail, and the rest is a backbone. So this is a backbone. This pink one is the backbone, and this is something like a branch, right? So this is how the monomer looks like, right? So I can certainly then use this to make the polymer. So I will say, okay, build a polymer. What is it? What do you want to build? Homopolymer, copolymer, dendrimer, random copolymer. So you can decide, just make a homopolymer. And we provide a library of polymers. So these are libraries where we have defined the repeat units. It could be ethylene. It would be depending on what library you are choosing. So there are not, there are some references, and these are you can reference in a paper that you have used it from a Material Studio database, and you can have lots of different options here. But here I'm not using the database. I'm using to my project, and I use this one as my reference. So I say this one is inside my 3D atomistic document, and this is my backbone. You use 10 of these to make one chain, 10 of these monomers to be arranged. And how do you want them to arrange? Is it head to tail? Is it head to head? Is it something on random? Is it something have a initiation group, have a terminator group? What is the torsion angle and all these things, right? So you can then, I said, okay, I just going to make it by head to tail, and it's a 10 in number. So this is my polymer chain. And what I mean by 10, and if I make it bigger, right? So what is 10? What actually is 10 is this, right? So it's a repeat unit select fragment, and it is a total repeat unit. So this repeat unit is combined 10 times to make this chain, right? Make this one chain available for you, right? So suddenly this is my polymer, and what I wanted to do was, I think it's my interest, and you can have different interests. You can see that this polymer I wanted to absorb on a surface, or I can make this polymer mix with another polymer. And I wanted to put it onto a surface and want to see what type of what is going to happen. And suddenly you may also, and this is something of your choice, depending on what you want to do. So here you want to see that I want to use this polymer as an adsorption over a surface. So I can go to a metal. I have a database, as I said, it's also have a database. So I go to a structure, I say metals, I say pure metal, I say, for example, copper. It's not that I love copper, but it's like it's a metal. And I say, okay, and this copper, I want to make a surface because this is copper bulk. This is an unit cell of copper. So you can see what is the lattice parameter, what is the volume, and suddenly you can make a bigger structure, right? So you can make a supercell. You can make it 3 by 3 by 3 so that its size get bigger. How do you know the size? So your initial size is this. This is the lattice parameter. This is 3.61, and you want to make it 4 times bigger than this, right? So you make it 4 times, and it's cubic structure. So you're making what you're making is 4 times 4 times 4. That means you're making 64 times. And if you go back, your number of atoms inside this lattice was 4. So you are now putting it 4 times 4 times 4. Then you know the number of atoms is 256. So you have a 256 atom structure, and this 256 atom structure you don't know, and you want to make a surface of it because you want to see an adsorption. So basically you have to cleave surface. So these are all Material Studio's visualizer or modeler can do. You want to make a surface. So you can say I want to make a 1, 0, 0 surface. I want to make a thickness of something, right? So I have a surface. I want to cut it from the top. I want to cut it from the second layer, third layer, wherever I want to cut. I want to make a thickness, which could be 1 unit cell, or I could make it a little bigger, depending on what I want to do. I can put some hydrogen on top, or whatever I want, right, in this model. But so I want to cleave. So this is my cleave structure. This is a 100 copper surface, which is bigger with a couple of layers. And then you want to add this molecule over it. This is 2-dimensional, so we will make it 3-dimensional by adding vacuum over it. And the rule of thumb is that if you the vacuum over it will be at least twice. So I think this one was 14 angstrom. I will just put 30 angstrom over it. So I see that this is something of my periodic structure. Now, you may say, why this is on top? This is an artifact. This is to show that you have a periodic structure and it has repetition all over the place, all around, and the lower atoms is technically there. So the vacuum you're putting, you have to be careful that there should be enough of gap so that this does not interact, right? That gap I have to maintain. So now I choose the atomistic, the atom we created, the monomer we created. I can add the polymer. I'm just adding it because of the size. So I can choose this molecule, say, okay, this is the molecule. And I choose it, I copy it, Control C. And then I say, okay, you are fine. You just be on the surface. I can see the molecule here. And then I can move it. I can move it wherever I want to move. I can rotate it. I can take it here. I can rotate this, right? So that means, like molecular configurations, they may come down to the surface. They may love it. They may do not like it. And if I can see those interactions in terms of absorption energy, binding energy, and those kind of things, right? So there are, and it could be anything, right? It could be anything and everything which you can think of that you can made up. We certainly have nanostructure. You can make single wall nanotube with different carbon lengths. You can make it periodic. You can make it non-periodic by adding more units on it, right? So it's a long nanotube with 24 angstrom, 2 nanometer by 0.8 nanometer diameter. So you can make these sort of rings inside, right? It's a nanotube. We also have lots of things in the database. As I said, there are metals. There are metal oxides. So for example, you want to have an alumina surface. These are gamma alumina. So I can see alumina surface. And these are tricky because in alumina surface, if I want to make a surface, I have to think of that whether my surface should be at the aluminium level or I will cut it at the oxygen plane. So if I want to cut it at the aluminium plane, it's at the same plane, but I can move it to an oxygen plane and cut it. And it is not just alumina, but you have lots of metal oxides, and you also have zeolite, semiconductor, but it is not all that every structure available is there. No. Why is it? Why didn't you put everything? Because when you put this data, it will use the memory, right? And so what we decided was we can import. It's a tool that you can import from any format, and it should not be our format. So if you see, if you see the bigger one, the PDB, you are seeing XYZ, you are seeing CIF. So you can have different format. We can certainly read it up inside Material Studio. So if I can search, like, I don't know whether I have something on here, but if I can search a zip file. I have a zip file. So I say, okay, where is this zip file? This is inside Todai, right? So okay, I will go there. I will go there, open file location, and I will go there and say, okay, I want to see this file here. I bring it up. And then it can open it up, the structure file inside Material Studio. Okay. Okay, if you can see it. And so certainly that's the value. So you can import different format of a structure. You don't need to really have the database increase it, right? So once you have the structure created, then you can do a lot of these calculations. And if I say, and these are different calculations. So for example, you have a 3D atomistic document. You can want to see, you can then choose what method I will be using, right? What I wanted to do. So these are all from the interface. You can calculate energy, geometry optimization, transition state if there are reactions you're looking into. There are LDA, GGA, meta GGA, hybrid, different functionals you can choose. You can choose if it's spin required, the charge, You can choose the electronic properties, the basis functions, and suddenly you can make a manual changes once you have the input file, but it's all from the interface, right? So you can say, okay, I want to do for 500 steps. I want to put some solvent, like a dielectric constant. I can use solvent with some dielectric constant, like water and or ethanol or a mixture. I can use that, and then we can calculate properties. And this DMOL is used for chemical properties, like it's a Fukui function, orbitals, it's reaction energies, it's kinetics, and all these. And we have another tool which is called which is periodic boundary condition. So you can use those kind of tools for spectral analysis, right? So if you are looking into Raman spectroscopy, because for example, you absorbed it, you have some water, you want to see what is the absorption behavior there, and you wanted to monitor that those are also possible. You can also use it like these structures. You can also use by molecular dynamics, right? So I can just show you that in a sense that you can run some dynamics calculation, and you can use it for a very small times a day, because I just wanted to just give you a demo of it, right? So I can put it into 5. And I wanted to calculate those dynamic steps. That means it's moving with a certain temperature. I can regulate the temperature. I can change temperature. I can also add pressure. And I will use. I do not want that copper to be dancing, so I can constrain it. I can say, modify and fix it up, so you can constrain it. And then I can run the dynamics. So it may say it is not actually optimized, and I will just leave it like that, universal. I can do that with Compass, but I just wanted to show you something is moving so that you get a better feeling of it. So technically, we have to geometry optimize it, and then we have to do the dynamics. I just want to show you something to see how things move over time, so that you get a feeling that what can you expect from these calculations, right? So these calculations generate different types of properties, and it will show you over time how things are changing. You can then calculate the diffusion coefficient and stuff like that, right? So, and this is a very small calculation. And so if you can now see, you can see an animation. You can see that by options, and you say make it a little smaller, slower, so that you can able to see it little better. And then you want to play that. So this will seeing that your molecule is moving, and I'm making it very, very slow, right? So, and technically you may want it to do like this, not like this, what the way I did. You may want to say that, oh, this top layer, I can just delete it because I wanted to see it from the top. I want to see it from the top. I make it bigger, and I because I cannot delete it. Because it's already calculated. So if I delete it, then the structure will be lost. But what I can do is I can hide them up. I can say, please hide it. So I do not want to see them, but I wanted to see it from the top, because that is where my experimental spectral data are there. My microscopy data. So now I can see like this, right? So I can see how this is moving over the surface over time, right? And then what you're seeing here is a profile. So if I see this, I will take this structure. I will take this structure and say this is a fragment. This is my set, and I will just give you to calculate. So this is the way that the system works, and certainly we can discuss over the questions that what you wanted to do, so that we can certainly we can say mean square displacement, and we can say I want to calculate the diffusion coefficient. So it will run this calculation to tell me how this molecule has moved over time. And this number is not, we cannot do anything with this because it's a very short calculation, but it gives you a number to a diffusion coefficient. So you know at some front, state front, that a molecule moved, and what is the diffusion coefficient of that one. And it is dependent on what properties you want, right? So this is for dynamics, but this is, like I said, gas step. Then you have to have band structure, density of states, properties like NMR, IR, Raman. Then you have to choose the quantum tools. So this is to give you a little bit of glimpse of how Material Studio looks like. and these would be parallel, right? So you can run these calculations. We provide a job license. So if you have one job license, so that means you can run these jobs into thousands of cores if you're accessible to. For example, if I have an access, I can run this in 280 cores. I can also support GPU so that I can get that speed also in my calculations. Okay. Now let us go back to where I'm talking. So I think what I will now do, I'll spend this time to tell you what are some of the examples on and to give you an eye opening or what can we do. So and this is something of a very very interesting piece that people industry where they're using catalysis for refinery, and where you have a refinery, you have an upstream and you have downstream, and you kind of try to find out that what will be the catalyst required, how it will be get separated, what is my optimum process conditions, what kind of feedstock I'll be using. And this is something you see that optimization-based approach for managing enterprise-wide business planning in petrochemical industry. They have been presented this, and it is many companies. And so if I think about it as I go there, you're looking into selecting a candidate, screen with modeling, designing experiments. This is from a catalysis perspective, right? Because you don't know which catalysis will work. And if it works, then you should synthesize, characterize it, and spend time on it. But if you do not, if you screen that virtually, then you save a lot of time there. So it's a normal discovery if you wanted to see that what can we synthesize, how can we synthesize a particular catalyst. So we can use these softwares like DMOL, VAMP. These are quantum mechanical tools to find out what is the energy of stabilization. And then suddenly you can do that from a database. You can create a database, and then you can recommend that which one they could choose. You can also use some sort of, so you are looking at a material any good as a catalyst or a refrigerant or a chip, then you're doing screening with the different properties. So you may decide what actually is an important property for a refrigerant. It should have a lower boiling point. It should reduce the viscosity. So you know the property, and then you calculate the property and see what actually changes these properties, so that you get an idea and use that for material behavior. You can also certainly look into the temperature differences, yields, efficiencies. You're looking into contaminants, you're looking at a degradation mechanism, and so these are the tools you'll be able to use it. So if you basically think of, as I was designing a surface, and if you are a catalysis guy, you probably know that anything should happen. If there is any reaction happen, there should be an adsorption behavior first. If it likes it, then it will be adsorbed. If it doesn't like it, it don't get adsorbed. So we first find out which is the hot spot on the surface of a metal oxide where you want to use it as a catalyst, and then you do a structure optimization for the adsorbed reactant and your other product, and then you do a reaction modeling. And we do provide with the reaction modeling to look at the kinetics, the reaction rate, and then you change ligand or you change your metal or crystal phase to see, okay, this might not be aluminum oxide or magnesium oxide. There must be a dopant here. This not be a 100 surface. They have a one reactant with 1:1. There is a reactant coming with 1:5. So how do I model it? So those kind of things you can test it. And this is an example, and I will give you a couple of them. And there are some paper references which you certainly can get later once you are, once we finish off this. So this is something to find out a mechanism of isobutene over 2-butene over HY zeolite, right? So this is the challenges. It's as you know, the liquid acid catalysts are used for the production of gasoline, but catalysts have negative impact, and replacing the solid catalyst with solid acid catalyst like zeolite, you need to know which zeolite will work, what sort of silica alumina ratio, what is the porosity of it. And so you are looking at alkylation reaction, so it can give you a hint to do this mechanism of this reaction. There are very important things going on coatings, like you want to find out the right coating. This is something on a ball, for example, or anything, right? You do coating for car, you do coating for your building paints, and any paints you think of, and it is dependent on solvent, it dependent on additive, it dependent on what actually, whether this paint you're using, is it something corrosive, as I talked about regulation, there might be some issue of regulation. You want to change it with some sort of change in the coating. This is another important aspect in terms of oil and gas. We are looking at enhanced oil recovery, where you wanted to see which one actually interacts with the oil molecules to get it, get it absorbed or coagulated. And so we try to understand the absorption behavior of organic ions on clay mineral surface, so that will design more effective fluids for the EOR recovery. So we design different surfaces. We define like bush type of polymer structure and see how these polymer structures react with an oil molecule or water and see what sort of bonding is happening there. This is an example to find out green solvents. If there are regulations because people wanted to change the solvents, because the solvents to be green, you cannot use acetone, or you cannot use compound which are which are not sustainable. So you choose different solvents and you choose a mixture, and your idea is to find out that which ionic liquid can be extracted well in what combination, and there are many combinations. You could be alkanes with alkyl benzenes or alkenes and alkaloids, and you can screen them and you can find out what will be and you can see that this is the maximum error, RMS error is 0.19 for all of these compounds. So you have a confidence in the method, so that and as I think I didn't mention, if actually experiment and simulation should not match, because they're different. We are going very close to experiment, so our target is to go close, and if it matches, then something is wrong, and that's an obvious. Certainly academically we can publish it, but if you are a maker and I said, oh, I'm not saying you to not do experiment. I'm saying you reduce your experiment. You understand what's happening, even if it is so in simulation we go around 2 to 5% of error most of the cases. In some cases we are very accurate with some properties, and then that will be your basis of it. And it's a similar example for refinery. You're looking into a fluid phase thermodynamics to selection of new solvents with desired properties to replace, because in columns, and you probably know if you're coming from a petroleum company, that how these solvents are detrimental. And we are providing you a thermodynamic property list of the different properties you are looking into. I will skip a bit. This is actually one example. It's a similar example, but this is focused on oil and gas. Now I will move into a little bit of downstream. So from catalysis to composite materials, and I think this is a trend of that's probably the future of polymer products. It's not, polymers are also modifying, and this is, I think, the best application we have seen with composite is airplane with Dreamliner, and that drastic change that happened. And what I show you in this demo, that you can start building your monomer, you can vary your polymer chain that will impact the structure. You build polymer, you make a mixture, then you choose what sort of properties you're looking. Is this polymer miscible? What is the solubility parameter? What is happening? What affects if I have longer chain length? What happens if I change additive with it? And we can also see that what sort of compositions, what sort of properties I'm looking into, a diffusion, a binding energies, and stuff like that. So if I can tell you about something on resins, and this is something very interesting. And if you see left hand side is what BIOVIA's Material Studio is up to, and this is the right hand side is what a macro scale. So what macro scale means, you have a device, you have a component, you have defined a polymer, you have defined a plastic by using that polymer, and you see there is a fracture at a certain pressure. How do we compare it? Can I propose this from simulation? Yes. So here you see we have done a resin, we have used curing agent, we make it, we look into the conversion, then we put it onto the surface and we calculate the stress strain behavior. What I wanted to see here is if I put it over a copper plate and I pull it, there should be I will be able to understand the fracture behavior. Depending on the conversion of this composite, I can predict what sort of deformation, what sort of impact in my mechanical properties are happening, and I can then pass this property to Abacus. That means I'm giving, Abacus is the name of a software from Dassault Systems, but what I'm providing is the material properties values, like the stress strain value, like the Young's modulus, the Poisson's ratio. Then the macro scale can adapt the material properties and use it to give a better number there. Okay. And this ideology, and this is something of a workflow, if you think of that, it starts with a resin where we have X-ray, IR properties, you create atomic model, then you perform a mixture, then you calculate properties like TG, CTE, and then you go to a mesoscale where you're going from nanometer to micrometer. And what now we are capable of, that if you do that in a mesoscale, then the mesoscale structure output will go into the macro scale. So so you are automatically connected into the macro scale. So you can define it like, if you remember, this is normally a macro scale where everything is spherical. And what you see when we have changed this from our simulation to Abacus, they are not spherical anymore, because polymers, it's resins, and their structure depends on the density. So this has been becoming non-uniform, and that will impact your calculation results. Okay. And I will just play the video to show you how it looks like, rather than what I'm showing was a demo, but it is similarly, I'm trying to show you that how we do it. Like, so you choose the, you are choosing and you're mixing these into a box. You're trying to see a reactions happening there. So let us see this, that you load the resin molecule, you find out what are the curing agent structures, and you are trying to level them, that what is your reactions, where the reactions will be happening. And then you are able to see what type of reactions you want to do. Is it a ring opening reaction? And so you can calculate a proper workflow, and these workflows are we created automatically. This is to run these calculations in that workflow to generate decided properties. So we created a workflow to calculate TG, calculate heat expansion. So that means what I mean by workflow is in calculations, you'll be mixing it, you're making an amorphous structure, you'll be running a dynamics, and so those processes over time I can decide on it, right? You can also add solvent, you can also add a number of molecules, a number of configurations, what species you want to use it. So yes, your name is there, and then you run these calculations with which type of reaction you're looking at. Is it a ring opening reaction? Is it and so that reaction is important, because it will tell you that which bond you are trying to look. So if you're seeing it, it's a ring opening reaction. So what you're seeing is epoxide to the primary amine, there will be a bond formation, right? So yes, so that's the bond formation you're looking into, and we'll be monitoring it. So you conform it, and then you run the simulation to generate all these all the reaction values for you, right? So it is now choosing the reactant. It is now trying to say, okay, I'm now looking into a dynamics calculation with a fixed temperature, fixed pressure, and I will look into a desired conversion. I decide 50%, 60%, 70%, so that I can see how over time things are get into a periodic structure, right? So then you see this over time, you're choosing it, and you choose your different settings. You can run parallel, or you can run it in your system. After time, it will tell you that the calculation is finished. You get the structure there. It has a network structure. Then you see the network structure. It will tell you, first of all, what you have done. So you know what are the setup you used, so that the next time if you change something, you have a record of it. And then you see the structure, that this is your bonded structure. Okay. And you can certainly vary a lot of things, and you can also generate a report where you're looking into temperature, you're looking into what sort of mechanical properties. So you get a report, and as you know, we are now in a world of machine learning. We are a world of artificial intelligence. So we require data, and these data could be generated by Material Studio. And this is an example probably to show you that how this connected story has a value. So it is a designing of a product. So if you think of that, this is a story with laundry pod. You know, laundry pod that has been used for detergent. This could be liquid. So this is a company, and this is what our value is. It is not just Material Studio, but we connected the story with data science and the laboratory digitally so that everything is connected. So now what you're seeing is a person in your company, for example, who looks into customer claims. So he has gotten information from a customer claim that there is something wrong in your non-laundry detergent. It is saying the children are eating our laundry pods. That's the problem, because the children's getting sick. Your product will be your product value will decrease. So he is noting this, and he wanted to let the product management know that there is an issue with it. So he created this, and he is now telling this to his. So this is a collaborative platform. Is going to a product manager who is looking into it. He will say, okay, what can be done? He looked into it. Okay, I get a note. From Chen that is telling me that yes, there is some issue. Oh, okay, let me do it. Let me have a look. So you're not responding an email, so that you don't need to go to email browser and all these things. You get connected, right? So and then you run it to find out if you have some idea funnel, right? Where you have done something before, you try to find out the ideas, and you see there could be an idea that there are a couple of ideas, and you may choose. You may think that, okay, let us make it harder so that they cannot chew it. They may have it, but if they cannot chew it, they cannot break it, then they may not get the detergent in, and they will not be sick. You like that idea, you take that idea to say, okay, let us do it. So let us now. So this is what you do in Abacus or simulation tools which are used for macro scale. Here they are putting an artificial object. They have created a pressure and say 308 Newton to break this. So now our job is to find out the composition which can make that laundry pod harden. So we want to mix a material, mix an organic molecule, or mix a polymer, which can be increase the hardening of it, right? So what I do here is you're looking now a machine learning to look into thousands of options from your database. And see that if there is something of a higher plasticity, if there is something with high mechanical properties, you can use some public database also. And you find out, okay, there are some molecules, yes, but they are not enough. I have to search it more. And I keep on searching it until I find out a right combination. And once I find it, and then I will try to identify, okay, so this is my water penetration, this is my mechanical properties, and let us build it. So now I will just use these tools to draw. So I will sketch it up as I did in sketching, and I want to use these molecules and calculate the mechanical properties of these molecules, a combination in a specific ratio, and we will mix them up. We will put this into a different temperature, different concentrations, and different range, so that I can then calculate simultaneously. I will also do a macro scale simulation, and I will capture all this information into a digitally placed an electronic lab notebook, so that the data is captured in an electronic lab notebook, where I can see both the data simultaneously. So this is your notebook. This is your polyvinyl alcohol with a plasticizer with an experimental name, and here is your simulation. This is the upper one is showing 302 Newton, and the lower one is saying how this behavior is changing over, and you can dig down and look into it carefully. So that's the combined story. That's the value of Material Studio. That's the value of simulation that you want to connect with your experiment and give value, so that innovation becomes shortened, right? So and what we wanted to show you, this is something that I probably have not able to cover all the things what we are doing, and we can do many other things, as we just show you a little bit of composite, little bit of catalyst. We also do additive manufacturing. We do a lot with perfumes. We do a lot with because you say perfume, you say cosmetic materials, because for example a shampoo, we didn't talk about it. There are references to say like, and there are companies like P&G, and they have published papers, and that's the reason I'm referring to find out a shampoo which can be useful for dry hair. So you have to make a lipid model, and you can test this hydrophobicity or hydrophilicity of a separate molecule, which can coming to this lipid bilayer surface, and that could be understandable by molecular dynamics calculations. And so you design that, you test that additive, and see how does that impact hydrophobicity. Because if you are looking for different hairs, oily hair, dry hair, you may do that testing for before you do a real experimental setup. Okay. And one more thing is that we do develop software, right? So it is a good point that and we develop and we yearly update our software. So what I'm saying is, based on our needs, we develop software, right? So you may see there are new functions in one tool. There is maybe the performance, we are making it much more faster, or we have generated new force field. So that's the way we create new tools to satisfy our customer needs. And we take a global survey, and we prioritize what we can deliver in that timing, right? So it's kind of to tell you that it has to tell you that what can we do by and what's our takeaways here. So I just wanted to give you that that message. So what you see here, we are covering up in different sort of industries, starting from life sciences. You are looking at delivering drugs. If you are looking at spin permeations, like you do some spin permeations because you know the animal testings are not possible in a lot of different countries. So how do you know that the efficacy of your drug molecule? Can it penetrate your skin layer and go into the affected site? You can look into like cosmetic, as I mentioned. It is to look into whether the containers are non-toxic. What is the shelf life of a drug and stuff like that. I talked about a little bit on energy and material. This is your oil and gas. You're looking at catalysis. You're doing downstream with polymers. And this is something of coverage with everything, where you have lighter, safe, sustainable products, and you try to make these products available. It also goes for high tech, where you're looking at battery materials, you're looking at semiconductor materials. But the whole idea is, if you know the structure of that, you can calculate properties. So you reduce your experimental volume by doing lots of computational experiment. And with that computational experimental data, you will be using that data to mastermind your next experiment, so that it becomes less time consuming, and it will increase your innovation. It improves quality and is reduce cost. I just give you a couple of our customers' comments, like understanding the mechanism of a behavior. It saves me a lot of dollars because I cannot do that without just by experiment. Develop and testing products in a faster environment is much more efficient. Less trial and error tests, and thus improvement of efficiency. Rationalized observations, hypothesis testing, introducing new viewpoint into thinking. Ability to understand the mechanisms which an experiment can hardly do, and we use simulations to answer questions that are difficult to answer by standard materials characterization. So it has an enormous potential, right? So I think if you are an experimentalist, and I do believe that you understand, and there are things which you cannot understand, that the reason of doing modeling is three, right? You should be doing it to reduce cost. You should be doing it to reduce time to market, your increase R&D productivity. It should be data driven and driven innovation and lower cost. And basically, if you're an academic institution, as you know, all and every publications now demand simulation, and it is not easy to get a software, compile it, and run it to get the results. Material Studio provides a fantastic interface. You can draw molecule, you can draw structure, and run the calculation, analyze the data. As I showed you, diffusion coefficient. Similarly, you see band structure. Similarly, you see density of states, and then you can able to get those things into your publications to give a lot of value to your publications. So our idea is, and I just told you the product scenario why I showed that video. It is just the whole connected story of your R&D, of your lab. It could be academic, it could be research, but if you're doing research, molecular simulation is a part of your workflow. It's a part of your lab, right? In lab, you have instruments, your NMR, IR, it is something like that. It's a tool which can help you to guide your experiment, give you answers which you do not able to get otherwise. Okay? So with that, I really thank you for your time and patience. And I am very open to have any questions you have. And feel free to I hope that you have some questions already in the chat. If not, you can just put that in the chat, or you can also, if you wish, you raise your hand, then I can unmute you so that you can ask the question directly, whatever way you want. So and as you have seen, there are handouts. These handouts are product content, so that you can know what Material Studio can do, what sort of what is the capabilities of it. And we are also having what do you call it, the products I showcased you today. You get an understanding of it, so that, and also our partner, who is our you know, as an interface, so that you can talk to them in terms of getting information to know more about it. So you can and send us questions through them. So with that, I think I will open for questions or comments. Feel free to ask me anything, and we have a team here, so you can even ask in Thai, and we'll be able to answer that. I'll probably try to understand from the team there, or you can speak, or you can write it up in the chat. So with that, thank you very much for your time and patience today, and I will wait for the questions.